All right, let's get right into it. Today, we're looking at something pretty wild, a new way for AI to see the invisible. And it does this using just two things: heat and the fundamental laws of physics.
So, let me ask you a question. How do you find a tiny, dangerous flaw hidden deep inside a solid object without cutting it open? It sounds like magic, right? Well, this is the core problem we're tackling. Imagine a supercritical part in an airplane wing or maybe a medical implant. What you're seeing here is the setup. You basically zap the surface with a quick laser pulse and then watch it cool down with a thermal camera. Now here's the thing. The way that heat fades away holds all the secret clues about what's going on inside. But the real trick? How do you actually read those clues?
Okay, so to really get why this new tech is such a big deal, we need to talk about the field it belongs to. Let's step into the world of non-destructive testing.
Non-destructive evaluation, or NDE for short, is, well, it's pretty much exactly what it sounds like. It's the whole science of how engineers inspect really important stuff to make sure it's safe without, destroying it in the process. Think of it like giving a jet engine a CT scan instead of performing an autopsy. You want to find the problem before it's too late.
And believe me, the stakes here could not be higher. We're talking about advanced materials in aircraft, high-tech 3D printed parts from medical implants, things where a tiny invisible flaw, a little void or a separation between layers, can be absolutely catastrophic. So finding a reliable way to see inside these things, it's not just some cool academic puzzle, it's a massive, critical safety issue. So why is this so hard? I mean, we have thermal cameras, right? Well, it all comes down to one simple and frankly super frustrating fact about the physics of heat.
This right here, this visual, just perfectly captures the whole challenge. Take a look. On the top, you've got a solid, perfect block, no flaws. On the bottom, there's a block with a defect hidden deep inside. But when you look at their surface temperature after you heat them up, they look almost identical. It's crazy. The evidence of that internal flaw just gets totally washed out, completely blurred by the time the heat signature reaches the camera. This is what scientists call a severely ill-posed problem, which is just a fancy way of saying it's incredibly difficult to solve.
The researchers who wrote this paper have a great analogy for this. They say heat diffusion acts like a stiff, low-pass filter. Now, what does that mean? Just think of it like the blur tool in Photoshop. As heat spreads out from the inside, it just smooths over everything. It blurs the sharp edges of a defect until it's nothing more than a faint, ambiguous smudge on the surface, if it shows up at all.
Okay, so the obvious next step, right? Throw some AI at it. People have definitely tried to use AI to kind of de-blur this thermal data and solve the puzzle. But those early attempts, they hit some pretty serious roadblocks.
You had two main approaches. The traditional methods were kind of simplistic. They looked at the cooling data one pixel at a time, treating each spot as its own little 1D problem. But that's not how heat works. It spreads sideways, right? So that method was just fundamentally flawed. Then you had the first wave of AI, these things called physics-informed neural networks, or PINs. And they were a step up for sure. They actually knew the rules of physics. They knew the heat equation. But, and this is a big but, they treated it more like a friendly suggestion than a hard and fast law.
And this quote from the paper really nails the problem. These early AIs used what are called soft constraints. Basically, the AI would get a little penalty for breaking the laws of thermodynamics, but it wasn't strictly forbidden from doing it. And in a really complex, stiff problem like this one, that little bit of wiggle room was totally fatal. The AI would just get stuck. It would find solutions that looked good on paper, that satisfied its math, but had absolutely no connection to what was happening in the real world.
Which finally brings us to the breakthrough. A totally new approach called neural field thermal tomography, or, much easier to say, NEFTI. So NEFTI's secret is that it combines two really powerful ideas. First, it uses something called a neural field. You can think of this as the AI's creative imagination. It lets the AI create a complete, continuous 3D model of the object's interior, not as a clunky grid of pixels, but as a smooth, elegant mathematical function. And second, it uses differentiable physics. This is its infallible logic engine. It's a perfect simulation of heat flow that's baked right into the AI's brain, forcing it to obey the laws of physics.
Okay, so here's the play-by-play. It's a loop. Step 1. The AI's imagination, the neural field, makes a guess about what the inside of the object looks like. Step 2. The logic engine, the physics simulator, runs a perfect simulation of how heat would flow through that guessed structure. Step 3. It compares its simulated thermal video to the real video from the camera.
And step 4, if they don't match, it intelligently updates its guess and starts the whole loop over again. It does this thousands of times, each guess getting closer and closer to the actual truth. And this diagram shows that beautiful, self-correcting loop in action. The AI proposes a 3D model of what's inside. The physics solver then figures out what the surface heat would look like for that model. It compares that to the real camera footage and then feeds the error back to the AI to help it make a better guess next time. It's just elegant. And this is the secret sauce. This is the game changer. Differentiable physics makes the laws of thermodynamics a hard constraint. It's not a suggestion, it's a rule. The AI is literally not allowed to break the laws of physics, ever. Every single simulation, every single guess, has to be physically correct. And that's what keeps the AI from getting lost in Fantasyland. It's what gives it the power to solve this incredibly tough problem.
So the theory sounds great, right? It's super elegant, but does it actually work? Let's take a look at the results.
So, after all that complex physics and AI, how well does this thing actually solve the case?
Honestly, the results are pretty stunning. Just look at this. The top row is the ground truth. That's what the flaws actually look like. Now look at the second row, the one labeled ours. That's NEFTI. I mean, wow, it's a nearly perfect reconstruction. Now compare that to the other guys. GridOpt is just this noisy, blurry mess. And look at PIN. That's the older AI method we talked about. It's a complete wipeout. It produced a totally solid block. It missed the defects entirely. And the numbers tell the exact same story. This table shows a metric called intersection over union, or IOU. It's just a way of measuring how accurately you found the defect. A perfect score is 1. Well, that old PIN method, it scores a 0.01. That's basically 0. NEFTI, on the other hand, scores a 0.45. That is a massive leap in performance. It's a level of accuracy that was just completely out of reach for any method like this before.
So what's the big picture here? What does all this mean? Well, this isn't just about a slightly better algorithm. It's really a new way of thinking about how AI can understand and interact with the physical world.
Here's what makes NEFTI such a big deal. First, you don't need big data. It doesn't need to see thousands of examples of good parts and bad parts. It learns what it needs to know from the physics of a single experiment on a single sample. It's also completely unsupervised, which means it can find flaws it's never seen before, flaws you didn't even know to look for. Plus, it can create these super high-resolution models without needing a giant supercomputer. And maybe most importantly, this whole framework, this idea of combining a neural field with hard physics constraints, could be used for all sorts of other problems.
And this number right here? This might be the most mind-blowing part from a technical standpoint. If you tried to do this the straightforward way, just to calculate how the AI should update its guess, it would take over 18 times gigabytes of memory. That's impossible on a normal computer. But by using a clever technique called the adjoint method, NEFTI does the exact same calculation using less than 22 megabytes. That's almost 1,000 times more efficient. It's what takes this from a cool theory to something you can actually use.
So that leaves us with a pretty fascinating thought to end on. We've just watched an AI literally learn to develop a kind of X-ray vision, just by watching heat patterns and being forced to obey the laws of thermodynamics. And it makes you wonder, right? What else can we teach an AI to see? What other invisible forces, what other fundamental laws of the universe can we bake into its brain? And what incredible new senses might we unlock by doing that?